Hi, I'm Matthew. Today we're going to be talking about different numbering systems, decimal, binary, and hexadecimal, as well as 2's complement. So to start off with, we're all very familiar with the decimal or base 10 numbering system, where we interpret each digit of a number as some power of 10. So we have our ones place, which is 10 to the 0, we have our tens place, 10 to the 1, and we have our hundredth place, 10 to the 2. And when you read a number like this, the interpretation is that you multiply the digit times the power of 10 and add them up. 1 times 10 to the second, plus 5 times 10 to the first, plus 5 times 10 to the 0th is 155. And in the decimal numbering system, it's base 10, there are 10 digits that we use, the digits 0 through 9. So now let's see how that applies to binary and hexadecimal numbering systems. Binary numbering system, you only have the digits 0 and 1. And it's base 2, meaning that when you see a number represented in binary, each digit corresponds to a power of 2 as opposed to a power of 10. So this is the 2 to the 0th place, 2 to the first place, 2 to the second place, 2 to the third place, and etc., all the way down. And the interpretation of this number is that when you see a number expressed in binary, you take, if it's a 1, you do 1 times that power of 2, and if it's a 0, you take 0 times that power of 2, so you wouldn't bother including it. And let me actually write out all the rest of these, just for the purposes of illustrating. So this number, if we wanted to take this number and convert it into decimal, we would add up all the powers of 2 that have 1s with them, because those are the only ones that contribute to the number. So we would add up 2 to the power of 7, we would ignore these 2 because they have zeros, 2 to the 7th, plus 2 to the 4th, plus 2 to the 3rd, plus 2 to the 1st, plus 2 to the 0th. And if you were to add all those up, you would see that it's the exact same as 155. And then move that to the hexadecimal numbering system. The hexadecimal numbering system has 16 digits. We use the normal digits that we know from base 10, 0 through 9, and we add in the letters A, B, C, D, E, and F. And those numbers, or those digits, correspond to the values 10, 11, 12, 13, 14, and 15, respectively. So this B here is in the 16 to the 0th place, because like base 2 and base 10, we take our base, or the number of digits that we have, raise it to a power, and that corresponds to each place in our number. When we look at this number, we interpret it as 9 times 16 to the power of 1, plus B represents the value 11, so that's 11 times 16 to the power of 0, or 1 in this case, and if you were to add that up, you would see that it's also equal to 155. So in this way, you can easily convert from binary or hexadecimal back to decimal. If you wanted to convert from decimal to binary or hexadecimal, you would just need to figure out how many powers of your base can be added into your decimal number and sort of construct your binary or hexadecimal number as you go. It's a lot harder to go from decimal to binary or hexadecimal than it is to go from binary or hexadecimal back to decimal. However, if you have a binary number and you want to convert it to hexadecimal, or if you have a hexadecimal number and you want to convert it to binary, the conversion is really easy. Because all you need to do if you have a binary number and you want to convert it to hex is look at groups of 4 and find the single hex digit that corresponds to that group of 4 in binary. And then if you put those together, that will be your hexadecimal number. So for example, in this problem, 1011 in binary corresponds to the value of 11, because that's 8 plus 2 plus 1. And like we said, 11 in hex corresponds to the digit B, because we have 0 through 9, and then 10 is A, and 11 is B. And in this case, 1001 is 8 plus 1, or 9, and that corresponds to the hex digit of 9. It's the same thing. And so the hex version of this number in binary is 9B, which is the answer that we had at the bottom to begin with. And of course, you can go backwards from that as well. If you have a hexadecimal number, you can convert it to binary by creating the group of 4 digits in binary that correspond to each digit in hex. And that works with any hex number, any binary number if you want to convert between them. It's the quickest way to go here to here or here to here. And now that we've covered that, we're going to transition to talking about 2's complement, which is the way that we're able to store negative numbers in binary form. So some trouble comes about when we want to represent negative numbers in binary. We've talked about how to represent positive numbers, but negative numbers are a different beast. If we wanted to represent both positive and negative numbers, one solution that we could use is if we were working with, say, 8 bits, we could have 7 bits correspond to the actual number that is being represented in binary, and then the leftmost bit could be 0 if the number is positive, or 1 if the number is negative. But that isn't a very good solution, because that means when you want to add positive and negative numbers together, you would need to compare their sign bits every time and then do addition or subtraction on those other 7 bits and figure out what you need to do on a case-by-case basis. The better alternative is to use something called 2's complement. 2's complement is a way of representing positive and negative numbers so that they can easily be added and subtracted from each other without having to worry about whether the numbers are positive or negative. And the way 2's complement works is you'll always have a fixed number of bits that you're working with in 2's complement. So let's say we were working with 4-bit 2's complement numbers. Our numbers would be 4 bits wide. And if we're working with 4-bit 2's complement numbers, we can express numbers in the range -2 to the third to +2 to the third minus 1. However many bits you have, it's 2 to the power of that number, -2 to the power of 1 less than that number, to 2 to the power of 1 less than that number minus 1. That's the range of values you can express in n bits of a 2's complement number. And the way you can interpret a 2's complement number is, let's say you have an expression like this, written in 4-bit 2's complement. Normally, we would say that this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. The only thing that changes in a 4-bit 2's complement world is this leftmost bit now corresponds to -2 to the power of 3. What that means is if you're representing a positive number in 2's complement, it'll be the exact same representation as it would be when we were talking about binary before. So if you had 0, 0, 1, 1, that still corresponds to the value of 3 in 4-bit 2's complement. However, this number no longer corresponds to what it would be in when we talked about it before, where this was 2 to the third, 2 to the first, and 2 to the 0th. This value is no longer 11. Instead, it represents something different depending on obviously what this negative is. It's -2 to the third plus 2 plus 1, which is -5. This might be a little bit confusing and unintuitive, but I'll give you an example real quick of why this is a good way to do it. Let's say we start off with the number 5, which is represented as 0, 1, 0, 1. And we want to obtain -5. The way you can obtain the negative of a number in 2's complement is you first invert all the bits. So 0's become 1s and 1s become 0's, and then you add 1. So this becomes 1, 0, 1, 1 is -5 in 4-bit 2's complement. The reason we like this is because now when we add 5 and -5 together, 0, 1, 0, 1 plus 1, 0, 1, 1, 1, carrying the 1 each time. And since we're only working with 4 bits, this last leading 1 just disappears. And when you add a number and it's negative in 2's complement, you'll always get 0 without having to worry about sign bits or doing addition or subtraction depending on what the numbers are. Now, keep in mind, like I said, that in 2's complement, you need to have a fixed number of bits. Because in this case, this is only -5 in 4-bit 2's complement. If we were working with, say, 8-bit 2's complement, this number would be, you can always imagine that numbers are preceded by leading zeros. Remember, only the leftmost bit has this negative sign. This would be -2 to the 7th, and then 2 to the 6th, 2 to the 5th, etc., etc. In an 8-bit 2's complement world, this value still corresponds to the value of +11 instead of the value of -5 that it is in a 4-bit 2's complement world. So that is an overview of 2's complement in general. Specifically, you should worry about how to take a number and convert it to its negative form in 2's complement, and make sure that when you're working with 2's complement, you always know exactly how many bits you're working with so that you know the actual value of the number that it corresponds to.